welcome to another mini lecture series sessions. Okay, so today we are going to do we're going to start dynamics. So this is the subject of dynamics. So far we have done kinematics, just talking about motion itself. We're not related motion, what causes motion. So it's been known, since before Newton. Actually, Galileo was the first one who figured it out that that for motion, if you have a uniform motion, so if you have an object which just move at say 35 meter per second with respect to say this is a pole which is fixed. So this is a fixed reference and this thing is moving at 35 meter per second. You don't need any cause for this. If this was like a vacuum, it will continue forever. It's like in outer space, it will continue forever. So this is like a uniform motion does not require any explanation. There's no explanation for it. Okay, it just is. For instance, if I were to, instead of this reference, suppose this was a train and I was inside the train. So now this train itself is not moving with respect to me. So as far as the pole is concerned, this also moving 35 meter per second. But if I were to write the motion of the train itself, that's the front of the train. Okay, the front of the train with respect to this. So this distance from me is say 50 meter from me at some time t1. Later on, train is over here, I'm still over here, and with respect to me, it still is 50 meters at t2. So when I look at it, so in this frame, so this is a frame called frame 2. When it's to frame 2, the train has zero velocity, not 35 meter per second. When I look at from one's perspective, it is 35 meters per second. Two perspective, it is zero. This is zero velocity. So what is the meaning of this number? There is no meaning. These are reference with respect to some reference. Okay, so that's law number one. So Newton's law number one is uniform motion, uniform velocity. Uniform velocity is uniform motion does not have a cause, does not require a cause to maintain it. There's been like a philosophical debate about what does it all mean. And so there's a kind of vague word called why it doesn't require that. It's just pick up a word, say, oh, there's something called inherent inertia. It doesn't give you any new thing. It just says, I can't, it's just arbitrary And so this thing is also arbitrary, continues to move because of inertia. Okay, it's just a way of saying it. Then if I have a non-uniform motion, this means acceleration is not zero. Okay, so if acceleration is not zero, what happens? So at some time, let's look at it. I have this, and I've got this frame. So this is a frame. I'm observing, first of all, every motion you need a frame to see if it's moving, not moving, okay? Or if, so at least you can say I'm going to look at the back of the train, so time t1, and over there at time t2, so this is the x direction, and this is the time t1, and same point in the train is distance x2. So, and then let's see over here. Let's go to x. Look at maybe you can set 0 time t. Let's put this t. I'm going to look at the 2 times t. Somehow you are looking at that, and then you have x3. So the distance traveled here is x3 minus x2 in time t, and the distance traveled here is x2 minus x1 divided by in t. Same time, if this is not equal to this, for any arbitrary places you place these times, okay? So it will be non-uniform. If x3 minus x2 over t not equal to x2 minus x1 over t, then it is a non-uniform. Because you have an acceleration, the velocity is not keeping its constant. So the other ways to non-uniform. If you go in a circle, say you going in a circle, where over here you're going that way, so that's the velocity direction. Over here you're going that way, so this is also non-uniform motion. So this sometime t, and this sometime t2. So this is a velocity at t1 and velocity v2. So velocity, even if speed 1 is equal to speed v2, v1 vector velocity not equal to velocity 2 vector, because this is also has direction, differs in direction. So this is the second law. Second law says that means the only way this kind of thing can happen is if there is a force, and it says force from outside the body, not inside the body, from other objects is proportional to the acceleration of the object. So at any time t, whatever acceleration is, it's instant by instant. So this begs the question, how do I quantify this force? Now, So this is actually how do you make it equal to quantify it? So you do go ahead and do some experiments and done by Newton as well as other people before him, that if you took say suppose you had a spring and you attached a mass and then you pulled it by a distance, so that now the spring is this big and you pull by distance, say 1 unit. So let's pull by 1 unit, so amount x, delta x, okay, equal to 1 centimeter, and then let go, and you said at this instant when I let go, time t when let go versus if I do the same experiment and if I pull delta x is 2 centimeter, same spring, then we find that when we let go and we say what's the acceleration here and what's the acceleration when I let go, we find that this acceleration is twice as much as that one. So let's call it acceleration in case 1 and case 2. So this acceleration I'm going to observe, acceleration 2 is 2a1. So it says this force, the spring's force, when I pull certain amount of length versus pull twice the length, I get twice the force. So this says, as for the spring is concerned, I have a way to quantify at least relative quantification. It's still I don't get to quantify fully, okay? So how to use this knowledge to make this equality is also possible, okay? So let's do the experiment number 3. So I do the same thing. So I pull it by 1 centimeter again and let go. So I pull 1 centimeter, delta x equals to 1 centimeter, and let go and observe acceleration. Let's call it, this time acceleration is a3. Just when let go. So at the very instant I let go, I observe it, okay? But do plots, etc. to make this observation. But this is a mass m. Maybe this is 1 kilogram. And so then I do repeat this experiment with same spring, but this one is 2 kilogram, and I pull again 1 centimeter. So at this point, whatever the spring is doing, so this force by spring, this force and this force, let's call this force 3. We don't know how much I've applied, but this is also equal to F3, right? So this F, let's call this F4. So F4 and F3 are equal because I pull the same amount. And why do we know they're equal? Because of this thing. We did the experiment. If we pull the same amount, you're going to have the same force. So we have a F3 here, and you have a F4 here, which is equal to F3. But what we observe is in this point now, when we observe at this point acceleration, A4 is actually half, because this is half of A3. So you can say that F3, if I were to make this equal, then I would be saying F3 equal to, say, some K. Looks like it depends on the mass, so let's put them. So F should be equal to, I'm saying acceleration is proportional to 1 over mass. So we can conclude from this experiment, x is 1 over mass. And of course, from the law itself, as acceleration is proportional to force, just keeping the direction out of it, 1 over force. It's just one dimensional, so just looking at the direction. So acceleration is proportional to 1 over mass times, this is axis of force, not 1 over force. Then make it equal, make it F equals to K times MA. Now this K will be independent of these things, independent of these three things. MFA. Now how do we set it? Well, now we go ahead and do experiments. K is something we don't know. So we would need to say how much force is a particular amount of force. So we can take this to say if M is 1 kilogram, and if I observe 1 meter over second square, then we will say this is 1. To make it 1, we'll say whatever the force on 1 kilogram is, we're going to call this 1 Newton. So that will set K equals to 1 by using these units. So we say if I apply a force F on a 1 kilogram object and observe it to have acceleration equals to 1 meter per second square, then I declare F to be 1 Newton or 1 N. So that's the way we kind of get rid of this K. That will be unit dependent thing now. So that's the second law. And it turns out this second law is not correct if so F in terms of vector will be mass time acceleration if M is time independent. So wherever we're dealing with mass not changing, then with this is not how Newton really wrote the original law, but this is the way we kind of study it now. To study a little more fundamental way or covers all cases, we introduced a momentum, introduced a concept called momentum. And this is what was introduced by Isaac Newton. And we use a symbol momentum vector. It is a vector quantity, but just called momentum. and usually a small letter like this is denoted because m is already taken by the mass. So this p is just randomly picked up. Okay, and we basically this combination mass times velocity, this is just this combination we're just calling momentum. And we now, if I take a derivative of that, then we'll have a dm dt times v plus m dv dt. So we see that this is can't do anything with it, so we just have dm dt v plus m, and that's the definition of acceleration from the previous lectures. You remember, take a velocity vector, take a derivative, and you're going to get acceleration. So we notice that that ma is here only because if mass is not changing, this must be not there. So we introduce f must be equal to just dp dt. So this is the general case, and this is the second law of motion. And this we say this guy is second law for mass is time independent, mass is not changing. Okay, so second law. Then there's a third law of motion, and there's a lot of confusion because of language. Okay, so here is Earth, and there's a satellite. So everybody knows that, say, this is the center of the Earth. So here's the force on satellite by Earth. So this is on satellite. But what you don't know is it wouldn't make sense. Third law says that there must be exactly same amount of force. This will be F on Earth by satellite. So if you look at these two forces, they will cancel. If I put it as one system, then they will cancel. So if you take because this is an internal force, if you take them together. So we say force, but there's always two forces between two bodies. So it has 2 points. There are always two forces between two bodies. They act on different bodies, right? This force acts on satellite, and this force acts on Earth. So these are two different forces. Their directions are opposites. Fourth, their magnitude is same. Magnitudes are equal. So this is the third law. What's the use of third law in problem, etc.? There's a lot of uses, okay? Fundamentally, the third law fundamentally third law has to do with conservation of momentum. And that we're gonna do some of the time. Don't have time to do this. See how we're doing with time. Okay. We're not going to do this today. Okay. So let's look at some of the use I can do. Okay. Here's a use. So uses of third law in F equals to MA problems. Okay. So it helps us find forces. Okay. In situations that easier to kind of not be able to discover. So here is a table, and say this is a book on the table, and let's call this is a rough. So say we want to find forces on this. So there is Earth here. So clearly there's a force called gravity that's going to act on it. So that's the force of gravity. That's one force. And Fg will be the weight. And then that's it. What's the other force? There seems like no other force. Then why isn't this going through the table? This is table, and let's see book. So we say, well, then these molecules here, which are next to these molecules here, they must be pressing into each other because of this force. And because there's pressing, if I blow it up and think of that molecules as little tiny springs, these springs are compressed. The springs are compressed. So when you have a compressed spring, so means these springs are compressed, and they are going to push out on, this is the book. And if you look at these springs, so this is the table and this is the book. These springs are compressed and they're going to push on the table. So there's actually a spring, this material is pushing against each other. And that's because this Earth. So these springs are compressed, pushing into each other, because this is being pulled down through by the Earth. So there's going to be this force. So this is F normal by table. And this is normal. And if you look at now the table itself, so there will be a force on the table, F normal on table. So let's call it make it prime, just to make it difference between this and this. Clearly, from the third law, the value of this guy and value of this guy will be equal. Fn will be F. This will be equal. Well, of course, the table. If you look at this is the room. By similar arguments, the table will have normal on table from here, double prime. There will be as many legs, you're going to have F triple prime, and so on and so forth. And the table has some body, and there'll be gravity on the table. So these will be the forces in the table. And these will be the two forces. What did I do? I made a mistake here. No, I didn't make a mistake. I actually pointed up. That's correct. So these two forces are the forces on the book. Now suppose you have the book and you have a table. You identify F normal from table, F gravity, and then you suppose you push, but it's not going anywhere. Well, if you're pushing, not going anywhere, that doesn't make sense, because this push will cause in this direction, when you break out F equals MA, and this is the X direction, Y direction, and then this actually is vector equation. So the X part equals to mass times AX, Y part is mass times AY, Z part is mass times AZ, right? So if I look at just this part, if acceleration is 0, then this has to be 0, but here is this guy is not 0. This has X part. These guys don't have X part. So I expect this not to be 0, but saying is AX is 0. Well, something is wrong. That means what's wrong is we must have neglected some force. So looking at here, so these molecules here and these molecules, they must be attracted to each other, kind of like a glue. They're locked into each other because of this pressure between them. So as opposed to spring, now they're locked, and this force will have to be. There must be, when I'm pushing it that way, there must be a force like this. So we just say that this is, there must be a force of friction. We call it friction, and this is called, because it's this not sliding, since not sliding, we call this kind of friction static friction. Now the static friction that we usually encounter is if you keep pushing bigger, and suppose you apply even bigger force, not going anywhere, another bigger. So bigger and bigger force you apply, eventually these adhesive forces, they have their ultimate strength and you break through. So if you look at in this case, if I apply FP and you say, hey, and you have a static friction, how big is static friction? Let's say I have a static friction and FP, their magnitudes, compare them. So this is 1, this is 1, it matches. Then I say 2 units matching. But if I say 2.5 units, and this is 2.5 units, if I apply 2.5 units, it actually breaks through. 2.4 units is matching, but between 2.4 and 2.5, somehow at 2.5 it starts to slide. So there is a amount I can apply, that's the maximum before sliding. So this kind of maximum, so this is, we'll call it Fs max. And that depends on how strongly they are dug into. So this dug into, this normal force between them is a reflection of how deeply they are dug into. So we say that Fs max must be proportional to how dug into each other are the two contact surfaces. Okay, and this is Fn between them. I'm not going to choose bitable, etc. Fn is between them, is a proxy for that. So this would be, the higher the Fn, the more the more it takes to push getting sliding. So we would just define it, max is a proportional, and make it equal to some coefficient is called coefficient of static friction. Okay, now what happens after this? Well, once it starts sliding, the forces are broken. So there's no more, there's normal, but there's, it's so say this is sliding. So when sliding, and say you are applying some force F push and sliding, and of course this gravity is still. Now if this all there was, so the acceleration is this way, acceleration, we're doing velocity this way, velocity is that way, and maybe acceleration is this way, maybe it's sliding with increasing velocity. Okay, so and so the acceleration is that way. So if you look at xy, now so the ay is 0. If you look at the acceleration, acceleration is all ax. Acceleration is all ax, and there's no ay. So if you look at the force along it, and there's along y, there's one here. There's one here. So if that was all, there should be acceleration, but there's no acceleration in that direction. So there must be normal still. That spring thing we talked about, that must still be, even if it's sliding, it must be enough time involved that pushing into each other, that still the table must be, the normal force from the table must still be acting, okay, on this. So in this case you will say, well, we got so what the way we summarize these forces or any of these places is you collapse the system in a dot and draw all, keep the same direction but draw from coming from the dot. So it's usually helpful to write down the coordinate along with it. So put all the forces coming out of, see, some origin of x y coordinate system, and this is the FP, all this coming into, we draw it like that. FG doesn't have a problem, draw vertically down, and Fn, instead of going into and pushing up, you draw from emanating from here, Fn. So that's a That's called free body diagram, and we're gonna, when you do problem, we're gonna do a lot of this. If I go back over this situation, for that free body diagram will be, I'm applying some FP, no AX, so this is the X direction, this is the Y direction, no AY, that made it FG, FN. So this will become FP along the x-axis and FG along the y-axis and Fn along that axis. But because no AX, and here is an imbalanced force, so it must be a force, exactly same amount of force in that direction. And that is this. So this would be a free body diagram for this situation. I will stop pretty soon. Just do one more free diagram, just that's going to show up quite a lot. So if the box is on an inclined plane, it creates a lot of confusion. You can see if I do recording, so I'm gonna have to restart this. So we were doing okay, so this so-called inclined plane problem, inclined plane problem. We do this because it's very captures a lot of different things. So here is a plane that's inclined, and this box maybe is being pushed down, and with the force Fp down the incline, and sliding. So what are the forces on this box? Well, there's going to be gravity. So this is the horizontal, which is same as that. Usually it's angle theta here. And here is a vertical. So the gravity is not that way. Gravity is going to be down this way. And Fp shown, but this, if there is a, in this point of contact, kinetic friction, because sliding will be up against the velocity direction. Sliding means is velocity is pointed that way. Velocity is pointed down the incline. Now there is a tendency to say the normal will be that way, but that's wrong. Normal will be, here is a surface of contact, normal will be 90 degrees to that. So here is the surface, and here's the box, and this is the surface of contact. So normal will be, if you take that a plane, then normal will be like that, and friction will be along this, and kinetic friction, if the velocity is that way, then kinetic friction will be that way. Okay, so that's, so if you write down the free body diagram for this thing, is going to be, you need the vertical straight down direction. That's the Fg, and you need normal to this 90 degrees. That's the direction for Fn, and you had Fp along this direction, Fp, and Fk that direction. And if this is theta, then this angle here has to be 90 degrees minus theta, and if you extend this guy backward, then this angle will be theta. So what we do in these problems, if this is what happening at instant t, in intensity, then normally we take this as the y-axis and take down below going like this as an x-axis. That will, what happens is acceleration will be along this direction, whether it's going to point it that way or point it that way. That's the acceleration this, or so if you choose coordinates this way, then only ax is not 0 and ay will be 0. So now we'll have to work out the components of this, and we are going to do this in future videos. Okay, I'm just telling you this is going to be a lot of problem, and we'll have to master this. That will be our next video, to master things like this. All right, so I'm going to stop it now. So take care. Bye.